This is Further Mechanics 1 from 2022. So the first question is about two masses that are going towards each other, one with speed ku, the other speed with u in the opposite directions. So after the situation, we have speed v and 2v. Now there's a couple of things that could be happening here, right? So this one is going faster. So it could be going faster in this direction, and this one is also going this direction, or this one could be going faster in this direction, and this one could have turned around. I'll deal with this case first. What couldn't be the case is this one couldn't be going this way, because then it would have had to pass through this one, unless this one was going this way as well, but since this one's going slower, that can't be the case either, because this one would have still had to pass through it. So there's either this, or there's the one with this going the other way around. We'll deal with that other case in a second. Find v and u in terms, find v in terms of u only. So we have the impulse here. Impulse is mv minus mu. We use this a few times in this paper, but we have the masses here. So we're just going to set. This is just on b, so this is going to be this one here. Of course, first is going left, so we'll set up a minus on this u here, which will obviously turn it into a plus there. And that will be that, I think, for there, and then we can of course rearrange that, and we'll get this, and then find the two possible values of k. This is where the swap in this potentially comes in. So we'll do conservation of momentum, so this times this, plus this times this, but this is a minus, remember, because it's still going this way, so that'll be a minus there, is equal to this times this, which is a quarter u, plus this times this, again with this being a quarter u, and the two I guess I've just written out here, but that's fine. We can, of course, solve this eventually and end up with k as 3/4, but then we have the other situation where v was heading the other way, and all that really does is just change this to a minus as well. So we get the same situation, but with this as a minus, and we solve that situation too, and we end up with k as 1/4, and so we have 3/4 and 1/4, and those would be our answers. Question 2 then, we've got a nice big picture here. Let's set up first that power is equal to, or force is equal to power divided by velocity, is the way that we can actually use this helpfully. So that's 12,000 divided by 9 is our force going forwards. So this is the picture. We've got force here forwards, got resistances here and here. We've got mg's coming down. Of course, those are useful because we have mg cos theta this way and mg sine theta this way. If sine, or alpha, if sine alpha is 1/15, that means thinking about a triangle with opposite side 1, hypotenuse 15. 15 squared minus 1 squared is root 224. So therefore cos alpha is root 224 over 15. You actually don't need that. I mean, this is 600g cos alpha and this is 600g sine alpha, but because there's no friction in this question, you actually don't need this. You just need sine alpha as this, and sine of this is this, and this was completely pointless. But anyway, I did it first and then just realized it was pointless afterwards, and I couldn't be bothered to delete my work. Anyway, from here we'll set F equals ma, of course, on the entire system. We've got our tensions in there as well, but yeah, F equals ma on the entire system says that this minus this minus this minus this minus this equals m, which is both of these together, a. We work that out, we get a as this, and then we can set up F equals ma maybe on just this part to get this minus this minus this minus that equals 600 times that a we just found out, and we can find t from there. I've given it to two significant figures because g has been used as 9.8, and that's two significant figures, so I've just rounded t to that as well. Question number 3 then, so we can break up this impulse into a vertical and a horizontal component. Of course, if tan alpha is 4/3, that means opposite side of the triangle is 4, adjacent is 3, that's the 3, 4, 5 triangle, so sine is 4/5 and cos is 3/5. And then this is, of course, is 3 sine alpha because it's opposite, so that's going to be 3 times 4/5, which is 12/5. And this is going to be 3 cos alpha, which is 3 times this, which is 9/5. And now we can do mv minus mu, and we can do it vertically and horizontally separately. So thinking about horizontally first, we've got the impulse, which is this bit here, is equal to mass times this, mass times whatever the final v is, minus mass times this. And we can solve for v, and we get this. And then we can do it vertically, right? So that's the finishing horizontal component speed bit. And then vertically we can say this is the impulse equals m times v minus m times nothing, because there's no initial vertical velocity or speed at all component of it. And of course this just leads to v is that. And then of course we can say, okay, well the speed of p is just this squared plus this squared square rooted, the two components, just doing some Pythagoras, and we'll get the speed is equal to this. Question number 4 then, so a few things to break up here. Let's break up these initial velocities into vertical and horizontal components. That will look like this. This will be 3u sine 30 because it's opposite. This is 3u cos 30, and so on. We know what sine 30 and cos 30 are, so I'll put those in a second. Let's first call, or before that, let's call the final velocity of a, just little a, and b little b, that just means that I know which one is which when I'm doing my working. We can, of course, write those causes and sines as what they actually are. So this is just me replacing cos 30 and sine 30 with the things they actually are. And then, of course, these two velocities can be broken down. Across is b cos 60, because that's next to the angle, and upwards is b sine 60. And across here is a cos alpha, if I've just called this alpha here, and a sine alpha going up. Now I can come up with a few equations here. Firstly, of course, sine 60 and cos 60, I know the values of, I can put those in. And now my equations, now this is conservation of momentum horizontally, I believe. So 3m times this one, plus 4m times this one, but with a minus, because this is going the other way, of course, is equal to 3m times this one, again with a minus, because I've got it going this way, and it must be going this way, it can't pass through b, plus 4m times this one here. And when you break that all down, you eventually end up with this, which doesn't seem very helpful until you then realize that the vertical components are preserved when this collision runs along the line of the centers horizontally like this. So this is equal to this, and this is equal to that, which is very helpful because that we can rearrange both these for a and b. This is a unbelievably stupid way to proceed with this question, by the way, but I'm just going to do it anyway because I didn't want to type up an entire another thing. I subbed that in for a, and I subbed that in for b, and I just solved this equation. Cos over sine is cot. All the other stuff is just numbers doing stuff, still numbers doing stuff, still numbers doing stuff. Cot is 1 over tan. You can flip both of these over and do tan inverse. So it would be tan inverse of 54 over 10 root 3. And you eventually end up with alpha as this. And now just be careful on this end point here. It's very tempting, because they've said this is turned through 90 degrees and 30 plus 60 is 90, that we just need to do 30 plus 72. However, what you want to do when you're doing angle that it's been deflected on is you continue your initial velocity through, and then it's this final angle you're looking for between where it was going and where it went afterwards. So we're looking for this angle, which is of course 180 minus 30 minus 72, which is going to be that. And it's just a coincidence, of course, that because this is 90, that means this is 90 on this other side as well. But yeah, this will be the correct angle. Find in terms of mu the magnitude of the impulse covered by b. So what I'm going to do here, I think, is I'm just going to replace these things up here with what I know them to be. I've worked out b is this thing, so I can replace this with that, and this is just, of course, this, as I've already said. Those two things are consistent, so that's fine. And now I think I can do some I equals mv minus mu for the third time in 4 questions, perhaps. And I'm going to do the same thing as I did before. I'm going to do it horizontally and vertically separately. So horizontally, we've got initial, we've got an impulse that I don't know, and we've got an mv. Mv is this times 4m, and then we've got this again going backwards, so that's going to change this sign, times 4m, and then we sort this out, and we eventually get this. And then vertically speaking, we have the impulses 4mu minus 4mu, which of course cancels, and we get no impulse vertically, which makes a lot of sense because they're colliding horizontally, which of course means the magnitude is essentially, well, I mean, it's this squared plus this squared square rooted, but we all know that's just going to make this. So that will be the magnitude of the impulse received by b. Question 5 then, I think we're halfway through. We've got another one where we've got collision across like this. So this is the initial setup, and we're told very little about the afterwards, but e is of course speed of separation over speed of approach. So what we can do here is we can say, well, let's just say that the final speed of this one is p and the final speed of this one is q, like this. And then we can say e is equal to, separation will be q minus p, and then approach will be 2u minus minus u. You go this one, and then this one, with some minuses. Of course, there's a minus u here because this one's going backwards. And we can say this is 3u, and we times by 3u, and we get this. Then we can think of conservation of momentum, of course. So 3m times 2u plus 4m times minus u, which gives us the minus there, is equal to 3m times p plus 4m times q. And we get this. I'm rearranging for p here so that I can shove it into there. So if we divide by 3 and then put it into there, we get this. Times everything by 3, I assume is what I did, it is. And then put these together, and you get this, factorize out and divide, and you get that, which is what we were being asked to show. After the collision with p, q collides with a vertical wall. So here's the vertical wall. And the coefficient of restitution there is a half. So if it comes in with speed q, it leaves with speed q, a half q, or q over 2. Cool. So okay, that's that done. So what's the range of values for e for which these two will collide again? Well, if p was positive, they would definitely collide again. But actually it's more than that, because say P was 0, they would also collide. And also if P was like minus 0.001, they would collide as long as that was bigger than that. Essentially, as long as P is bigger than minus a half Q, I think we're fine. There doesn't need to be a bigger than 0 here. I don't know why I typed that, because it's of course allowed to be positive as well, because I think I typed this up because I had previously done it separately, but we don't need this. I'm just doing it in one go. So we don't need this here. We just want to be bigger than minus a half Q, because say if P was minus Q, this would be going this way faster than this was catching it up. So we just want to be bigger than minus a half Q. I don't care about the second thing. So of course P is this, given what we worked out earlier. I can substitute these two expressions for Q into here and here, and eventually I can solve this for E, I believe, because all of the U's cancel out eventually, which is really nice. And I'm just doing some stuff here. It's not very complicated. We eventually end up with that. Make sure you always include E bigger than 0 at the end. If E was equal to 0, then when these two things collided, they would just stay where they were, and of course you'd never get another collision, so E has to be bigger than 0, and less than this, of course. Just follow through the maths there if you're a bit unsure. I've just done some basics, regular stuff there. Anyway, again, then I can simplify that up, I guess. Okay, so question number 6 then. So we've got a few things going on here. It's an inclined plane, which is obviously incredible to see. Tan theta, again, we've got this idea, 3 over 4, so 3, 4, 5, and then 3 over 5, 4 over 5 for sine and cos. Good. And then we've got, it's asking us to find the potential energy lost by this falling 3 meters. So if this falls 3 meters down, this object has lost 4 times g times 3, which is 12g joules of energy. But this one has gained, right? It's gone 3 meters up this diagonal here, because this has dropped down 3 meters. But then, of course, that's not a rise of 3, because this is a vertical rise of h. So we need this length here, of course. If that's theta, that's theta. This is 3 sine theta. Sine theta is 3/5. That would be 9/5. So the potential energy gained by this one is 2 times g times 9/5, or 1.8, just because I couldn't fit it at the bottom of the screen. And then we do the amount lost here times added the amount gained there, taking away the amount gained, and we get a difference of this, and that's the energy lost in total. That, I don't think that's how you spell that, but I don't care. Kinetic energy gained then, so we're looking at the next system, I guess, the next question, I guess. Given the speed of v at the instant histogram is that. Okay, well that's important, because that means the speed of a is also that, because this string is inextensible, I think it says somewhere. Good. So use the work energy principle. So the kinetic energy gained is half mv squared here, and also half mv squared there, where the v's are the same, 4.5. So we've gained that much kinetic energy. We've lost this much potential energy, which I can write as a decimal now, if I want to. And so that's total energy lost of one minus the other, which will give us this. That's our total energy lost. Using the work energy principle, we can say, well, the work done is by friction, of course. So we've got mg coming down here, which is just 2g. We've got 2g cos theta this way. Cos theta is 4/5 times 2 is 8/5. We've got an r of just 8/5 g as well. And so our maximal friction force is mu times 8/5 g. And that's going to act for 3 meters as this moves up the slope. So 3 times this is equal to the energy lost. And of course we can solve this for mu using g as 9.8, and we get mu as this. Possibly given that's too many decimal places, given g is only 9.8, I might have got away with it, I don't know. Anyway, we have mu, and then after b hits the ground, so it's hit the ground now. Let's just pretend this has already gone up 3 meters, and now we're looking for the extra length d that it goes up before it stops. Now we can just do work energy principle on A here to get these marks. So the kinetic energy lost, the moment that hits the ground, it's going 4.5 meters per second. So kinetic energy lost, it's going to finish at 0 meters per second. So we're going to lose all of that kinetic energy. We're going to gain some gravitational energy though by doing another triangle here. D sine theta is across here. Sine theta is still this. That's going to be 3/5 d. And so the gravitational energy gained is mgh, where this is h. M is of course 2. So we gain this much, which I could have just typed into calculator. Oh no, I couldn't, because I don't know d. And again, that's equal to the work done times the distance. This is the work done times distance there. And we know mu is 0.4, whatever it was, so we type that in, we type some more stuff in, and eventually we end up with this. And we have that whole question done. Fantastic. Question number 7 then is one of these ones where you've got a mass hanging down from a ceiling, and it's on a stretchy string now, and it's stretched to 3a. beyond, I mean, its regular length is A, so it's stretched quite a long way, and now it's being let go, and it's going to bounce back up because obviously it's stretched so far. So the force is, of course, mg. We've got a tension coming up here. This is just the formula for tension. And but first, I think what we want to deal with is energy. So right now, think about how much energy is stored in the spring. We're asked, it comes to instantaneous rest at A, which is the point right at the top here. So it's going to gain 3A meters in height. I guess if that's in meters, I don't really care. It's going to gain 3A in height. So that's going to be, so the potential energy gained is m times g times 3A. And this is the formula for elastic energy. It used to have this amount of elastic energy because the stretch is 2A because it has natural length A and it's being held at 3A. So the stretch is 2A. And then what's this? Well, this is a spring, right? This is a spring. So when it goes all the way to the top, it's going to be stretched A. It's going to be squashed by A, right? Because it's got natural length A. When it goes all the way to the top here, it has length 0, if that's even possible. So its stretch is going to be A. So this is the amount of elastic energy lost going from here to sort of equilibrium, and then we're going to take away the amount that we gain by squashing it up a bit more. So this will be our energy balance equation. We can sort this out. We'll eventually end up with lambda is what they want us to get. And then show that P attains maximum speed. Maximum speed what happens when it's at its equilibrium point. That's just a super useful thing to know going into this paper. So doing F equals ma here, equilibrium of course means A is 0, so we want this to be equal to this. So let's just find the x for which this is equal to that. Of course, lambda is 2mg as it's given me, so x is A over 2, which is just very, very nice to pick up those marks. Use the principle of conservation of mechanical energy to find the maximum speed. So maximum speed, we can obviously do exactly what it says here. So we can say potential energy gained. Now we know that it's at its maximum speed when we're at a stretch of a half A. So we were at a stretch of 2A, so we've gone up 1.5A to get to that half A point. So the rise is 1.5A, so potential energy gained is m times g times h, which is 1.5A. We've lost some elastic energy, right? Again, it used to be stretched 2A, so that goes in that formula, and now it's only stretched to half A, because that's where we found it needs to be. So we're going to take away that amount of stretch there. We get this as our total elastic energy lost. And then we also have kinetic energy gained, which is of course just half mv squared, because it has initially no velocity, and it has final velocity this, which is what I want to get. And of course by conservation we know that the gains, this and this, must equal the losses that, and we can have this as our final answer. In reality, the spring is not light. If the spring wasn't light, it would have to be factored into our potential energy gained scenario because the m's would have to add up. When it says affect your energy equation, you have to pick something in here to change, and it would obviously change this one, right? Because it would have to go into the m there. So that's, I mean, it was the first thing on the list, so it was just the first thing I saw and the first thing I wrote down. 8 then is a speciality, an R2 duty speciality to deal with these walls that are like this. I'll get to it in a second. Basically, I have no idea what the proper method for doing this is, so I just do it a different way, which I think makes a lot of sense and works really well. So I just do it every time. Anyway, going into this, we have a vector 6 minus 8. So that's 8 downwards and 6 across. When you collide with a horizontal wall, this component velocity remains unchanged. So that's going to be 6 across, and then we've got a coefficient of e, which means the velocity going upwards is just going to be 8 times e. Now this is kind of a cool question. Find the range of possible values for e. It seems like you haven't been given almost any information for doing this, but what you need to realize is if this was like a perfect collision, this would go upwards, if e was 1, this would go up 8 for every 6 it went across. And now the problem with that is that that's too steep to actually connect with this, to hit this wall again. This wall is shallower. This wall is going across 2 up 1. So what we need is the gradient of this line to be less. I don't really need this theta. I was thinking about using trig, but we just need the gradient of this line to be more than the gradient of that line. If this line is too steep, it's not going to connect. Now the gradient of this line is of course just 1 over 2 because it's across 2 up 1. So the gradient of this is 1 over 2. We need 8e over 6 to be less than that. Right? We just need this gradient here to be less than that gradient. So 1 over 2 needs to be bigger than 8e over 6. And this very quickly gives us the e value that we need. Find the full range. Of course, we need e to be bigger than 0. If e was 0, this would just hit this wall and just die. So we need e to be bigger than 0, and that will be our range, which will be good. It's given now that e is a quarter. Okay, so 8 times a quarter is 2, so I'll replace that with a 2. And the coefficient of restitution between these two walls is a half. And we want to find the velocity of b immediately after the impact with st. Now this is where I'm going to do my thing, because I don't understand how to do this properly. If you've got a diagonal wall, basically all my logic is wouldn't it be nice if that was just a horizontal wall, because then you could just do this and it's super easy. So this has, we'll call the final thing uv, which we'll find later. This has vector 2, 1. So what if I just broke out my core pure rotation matrix and just rotated this line and all of this entire scenario? I can ignore all this, don't need it. But what if I just rotated this entire scenario to make this a flat line? Okay, okay, well this theta currently is, tan theta is 1 over 2, because that's 1, that's 2. So tan theta is 1 over 2. You could do inverse tan to find the angle, but that's what plebs would do. So we imagine this being 1, this being 2. 1 squared plus 2 squared is 5, so this is root 5. So sine theta is 1 over root 5, and cos theta is 2 over root 5. So that's that. And now I can put those values in. Now the only problem is this is an anti-clockwise rotation, and I want to ideally turn it clockwise to make this horizontal, but I'm pretty sure to turn clockwise you just need to put this minus here. And in fact, I don't need to be pretty sure about it. I can just test it. Right, so I'll put my cos thetas and sine thetas in here, and then I'll just times it by 2, 1, and we can see this times 2 is 4 over root 5, plus 1 over root 5 is 5 over root 5, this times 2 is minus 2 over root 5, plus 2 over root 5 makes 0. And this is a nice horizontal line, isn't it? It's going across with this, up with this. So that's a nice horizontal line. So I'm aiming to change this entire situation into this, using this matrix, except I actually won't, because this is an annoying matrix to use. So I'll just take out the root 5s and just use this. And you can verify that this times by this also makes something 0. In fact, it just makes 5, 0, right? Which is fine. It doesn't matter that there's this scale factor missing, as long as it makes it horizontal, that's good. So okay, let's change 6, 2 using this matrix. So this times 6, 2 makes 12, plus 2 is 14, minus 6 plus 4 is minus 2. So this, in this universe, is going down 2 across 14. And then what we can say is this 14 remains the same. This is why I wanted this to be nice and horizontal. And then this here is just 2 times e, but we've been given e as a half, so that's just 1. So this vector here is 14, 1. Now that's of course not the answer, because this is in my made-up horizontal world. So what I need to do is I need to say, well, this matrix here times by this would give me this, right? So therefore, if I front multiply by the inverse of this, I'm going to get this. You could type this into a calculator, or you could just remember how to work out the inverse of a 2 by 2. You swap any negatives that are here, and then you swap these two over, which isn't going to do anything. You get this. You also do 1 over the determinant, of course, at the front, 1 over 2 times 2 plus 1, which is 5. And then, of course, we can multiply these together, and we'll end up with this here, and that will be our answer to this question. Thank you so much for watching, and I'll see you next time.